Welcome to another episode of the Corrosion Journal interview series. My name is Sammy Miles, and I'm the managing editor-in-chief of Corrosion Journal, AMP's peer-reviewed scientific journal. We're continuing our series on corrosion and health with today's conversation on the antimicrobial properties of metals. I'm joined by Harold Michels, a consultant, and John Scully with the University of Virginia. Thanks for joining me today.
Our pleasure.
Before we dive into today's discussion, can you provide a little information about yourselves for our listeners? And let's start with you, Harold.
Yes, I spent almost 30 years with the Inco Limited metals and mining company that mined copper and nickel and made alloys, mostly nickel-based alloys. And then I spent another 15 years with the Copper Development Association, where I managed projects that defended copper markets and found new applications for copper.
Thanks. And how about you, John?
Well, first, hello, everyone. Thanks for looking at this podcast. My name is John Scully, and as many of you know, I'm a professor at the University of Virginia and the co-director of the Center for Electrochemical Science and Engineering. Before coming to UVA, I worked for Naval Ship Research and Development Center, and I worked at AT&T Bell Labs and for the Department of Energy at Sandia National Labs in Albuquerque, New Mexico.
Wonderful. And I'd like to start our discussion today defining what we mean by the word antimicrobial so that we're all on the same page. So can you provide our listeners with a brief description of the term and what it encompasses? And Harold, do you want
me to start? I spent a good number of years working on the antimicrobial properties of copper, but I looked at other metals along the way. And what we meant by antimicrobial is that the copper surfaces have the ability to inactivate and kill bacteria and other microbes, including viruses and fungi. It requires no human interaction, and it's just a passive system that's in place and works 24/7.
Yeah, that's right, Harold. It's something that's distinct from artificial man-made cleansers where you might have to apply it periodically every 24 hours, and then it doesn't work if you wait long enough. And so this turns on and turns off naturally, as you've mentioned. And Sammy, I believe that antiviral is got a similar definition. It's inactivates viruses. I don't know if it kills viruses, as has been mentioned, but it inactivates the virus or it inhibits viruses. And also the antimicrobial, particularly pathogenic organisms that are harmful, these bright materials can inactivate.
Great. And which metals have antimicrobial properties, and what actually triggers those properties? I mean, does it just work, or is there anything that makes it happen? And we can start with you again, Harold.
Basically, the mechanism is not completely understood, but I think we have a pretty good idea about its mode of action, particularly with copper. We really didn't go into detail with any other material, but if another material is antimicrobial, I suspect it would have some similarities. Essentially, copper in particular has the ability to exist in two oxidation states, and it acts as a catalyst. And when it's going back and forth between the oxidation states, hydrogen peroxide can be formed. The two oxidation states are cuprous and cupric copper, or Cu+1 and Cu+2. And the action occurs when the bacteria come in contact with the copper alloy surfaces. The copper catalyzes the formation of reactive oxidation species, and hydroxyl ions are formed by something called the Fenton reaction. And the unpaired electrons in the hydroxyl radical are highly reactive to cellular surfaces, particularly lipids. And it disrupts the cell wall integrity. And interferes with respiration and metabolism, and the cells die. That's it in a nutshell. It's very complex what I said, but you can go through it step by step, and it does explain it, but I don't believe that's the full story.
Right, and just to add, thanks, Harold. That was an excellent explanation. You know, the antimicrobial, you know, we generally copper and copper alloys, you know, but also silver is thought of as an antimicrobial material, and you'll see silver used in various applications. Other thing I just want to mention is there are a lot of applications where people have embarked upon antimicrobial efficacy, where they've tried copper oxides or copper oxychlorides or some sort of solid species that in contact with a moist environment or like human sweat, if it's a touch surface, they will release the copper ion. So you'll have, as Harold mentioned, copper +1 and copper 2+. And those cuprous and cupric states, you know, revert back to what Harold said. They have this function they can serve to disinfect. But I just do want to mention there's about 11 patents, I think, on basically, like, for instance, even glass with high touch screens and high touch surfaces can have the copper oxide. You might say, why does the copper oxide work? Because it's already taken away. The corrosion step has already taken place. Like if you embed something like the copper oxide. So you will see in some applications, people have used these copper oxides, and there, it's not in the corrosion, you've got to have an anode cathode, and you've got to have an electrical and ionic path between the anode and the cathode. But when you have the oxide, you've already created the cupric and cuprous ions. And so subject to the chemical stability, they can release the copper 1+ and the copper 2+ in the right environment. And then if that environment dries up or goes away, then they would stop. And so it's sort of stored as a reservoir that's available. And I just think that's the other part that's missing. There are other kinds of things, like the titanium dioxide is a photocatalyst that actually basically splits water. And so you get sort of the oxygen radicals and oxygen and hydrogen out of that reaction. So that's an altogether different process than the one we're talking here, although it is an electrochemical process. But the main source is the copper ions from a corrosion process, where you've got some cathodic reaction and some anodic reaction, which is the dissolution of the copper. The one thing about the silver that's really unknown is that in some of the applications, why should silver oxidize to form a silver cation? And so people have embarked on using like silver nanoparticles, and nanoparticles will corrode faster than, let's say, a flat slab of material. And so you can get this nanoscale corrosion where you release silver 1+ that might occur from a nanoparticle, but might not occur from a large flat surface of silver.
Thanks for the explanations. How have we used those properties throughout history?
Oh, well, there's the earliest reference we can find, at least I could find, is something called Smith's Papyrus, and it's from 2600 to 2000 BCE, before the Common Era. And basically, Smith happened to be a book dealer. That's not an Egyptian, but he found this papyrus, and it mentions using a green pigment, which is more than likely malachite, which is copper carbonate hydroxide, and it's used to treat wounds. So that is one reference we found, and there are others after that. Certainly the Greeks, the Romans, and the Aztecs had similar reports found here and there about using copper chemicals and even metallic copper for skin infections. And so these are pretty, most of these cultures are warriors, and they were treating a lot of wounds, and they found that they actually were pretty helpful. But the most recent work that I can find that referenced copper was basically, during a cholera outbreak in Paris in the 1860s, they found out that copper workers, which I assume they mean coppersmiths, were not impacted by cholera, but the general population was. So there are lots of reports. There's a famous Roman surgeon that had very low infection rates, and he used bronze instruments, which was quite common in that era. So there are things in history where people have used it, but this was before the germ theory evolved by Pasteur. So once antibiotics came on the scene, people lost the knowledge of using copper for these applications. However, there was a professor of nursing in a hospital in Erie, Pennsylvania, named Phyllis Kuhn, and in the late 90s, last century, did a study on doorknobs, brass, aluminum, and stainless steel doorknobs with their maintenance people to show them how to improve hygiene, and they found very little bacteria on brass, which is a copper zinc alloy, and lots on aluminum and stainless steel, fine materials, but they really didn't have antimicrobial properties. So that's how when I found that paper, when I joined the Copper Development Association, I decided to pursue that, and that led to the antimicrobial project at the Copper Development Association.
Right on, Harold. I mean, I agree totally, and I think it's you captured the history very well there. You know, just on the water purity, it's always interesting to me. It's kind of come full circle. But so when the ancients used bronze for the water storage, you know, they had some natural capability to water disinfect or water purify that they didn't realize, but was effective. Then later, you know, in places where plastic containers have been used, as you've mentioned before, they don't have this natural, no human intervention supply of the copper cations. You know, that you mentioned wounds, and that just underscores how, you know, since people use these copper compounds, these corrosion products, that just underscores the utility of the cation, even if it's already stored in some sort of oxide. So they also found that was useful for skin ailments, as I recall, that people would put that on various rashes and whatnot. And then, of course, that's a little bit later. It's after all these. So Harold's right on, he's a reservoir of knowledge on this. But the ship hulls, you know, and during the time where navies became really developed and speed was a factor, the ships with the copper sheathed hulls, you know, could go much faster. There was much less anti-fouling than the other ships that did not have this or that had wood. They were much slower and couldn't maneuver. And if you go back into old history, in the not as old as Harold was talking about, when you talk about the Dutch Navy or the British Navy, they remark on how fast the British Navy could go with these copper sheathed hulls, serving as something for anti-fouling.
Well, certainly the British won many battles because of the copper clad wooden ships, because they could go faster, and they didn't have the problems of the teredo worm decaying the wood in comparison to their Spanish and French competitors.
Yeah, I guess it's great. So people, you know, trial and error is a way we'd like to think of advanced engineering as, you know, designing our things by computer modeling, but it's been found that copper interfered with bronchitis, poliovirus, HIV, influenza, cholera, and a lot of these were by serendipity, like the copper workers, probably, coppersmiths at the time.
I want to circle back quickly to the comments on water and disinfecting water. If it's stored in copper versus plastics. Did you have anything you wanted to add on that topic, Harold? Because I know John mentioned it, but
yes, copper certainly has advantages, but I have not seen, I would say, definitive studies that Copper is a very good material for plumbing. It lasts for decades. It doesn't fracture in earthquakes and things like that versus plastic. But I don't know if the antimicrobial properties are really a factor because of the residence time of water molecules in a pipe flowing when people are drawing water for drinking or cooking or what have you. It's very complex, and I think under certain conditions you might get something, but I think it wouldn't be generally something you could advocate that copper plumbing would benefit your health because we're killing bacteria. Bacteria shouldn't be in potable water in the first place, so I don't really see the application there.
Yeah, the one thing that I would add to that is that, of course, I agree with Harold on this copper piping issue and the residence time, and so in the applications where it seems to have worked, it was more water storage. And in the example, so we have a professor here, Jim Smith. He's published a lot of work on this with this project called MadiPure, and it's for these very poor communities in Africa that can't disinfect their water, and it particularly affects children, who get these intestinal tract type ailments and stuff. And so what he has pioneered or what he has championed, it's probably not new as we call it in science, but he takes a ceramic pellet, picture something bigger than the size of a Frisbee, that he impregnates with either the silver nanoparticles or, as I suggested, to try copper nanoparticles and also copper plating. And what he found was that, as we mentioned before, the silver seems to work by a similar mechanism, although some of the details are elusive. The silver nanoparticles worked very well. However, silver is too expensive for the communities to afford. And so I really tried to push the copper. And what they found out was that the copper was not as effective as the silver. And they seemed like they needed more copper cations, the cuprous and cupric ions that Harold mentioned. And so then they came to me, they wanted to hook up a battery, and they wanted to basically corrode the copper at a faster rate, because everybody knows you can corrode at a faster rate if you take certain considerations and make it a driven electrochemical cell. And so they tried that, and then they've tried to make the copper effective, but it's not as easy because that requires the human intervention that Harold mentioned at the beginning. That requires that you have batteries that work, that are fresh, that are said. So that's right where that project stands. And so in that case, they do see it's a pretty direct effect when they can test that by just dropping in copper chloride instead of waiting for it to be released from the copper nanoparticles. And they can see that they can disinfect the water that way. But it's making it work without human intervention that's the real troubling spot.
John's statement about water triggered my memory a bit. And I came across a professor who was when I met him, he was at the University of Northumbria in Newcastle in the UK. And he ran laboratory studies and field studies in his lab in the UK and also in the Punjab in India. And they were measuring E. coli in water. And they also have a similar problem, but it wasn't copper versus, they used to use copper and brass in particular, but now they've gone to plastic because it's cheaper versus copper, and it's not a problem most of the year when they have sunlight because they get solar disinfectants of water, but during the rainy season when they don't have sun, the bacteria multiply. The people are drinking the water out of the plastic vessels, and they're getting sick, and they get so sick they can't work. So it's affecting their livelihood. But if they went back to copper and copper alloys, which he demonstrated, that they wouldn't have this problem. And just, you don't need a whole vessel made out of it. You could drop in, a disc of copper, and that would give you some protection. But they did measurements And they found out in 6 hours that the bacteria were gone in the copper vessels, but they were still present in the plastics. And I found people of Indian extraction tell me that yes, they remember their grandparents used to serve water in copper vessels, and you can buy these copper vessels today. And I actually gave them out at one event. They were kind of interesting, and traditionally they had a solution, but it went away because of economics.
Yeah, those are interesting stories, and that's great to hear that depending on how you're using the metals, whether it's as a storage versus if it's just piping with potable water, there is a difference on the effectiveness. I want to continue forward. Has there been more focus on using silver and copper and other metals with antimicrobial properties more recently? So with events like COVID-19 pandemic, where we're all concerned with viruses in the air and on surfaces, and has COVID-19 changed how we're approaching these materials? And we can start with you if you want on this one, Harold.
Sure. I actually had retired before COVID-19, so I didn't have to go into New York City on the subway and etc. And I thought about it a lot, and I was in contact with my colleagues, and we had some interesting information on speculations about COVID-19 based upon work done by Professor Keeble at the University of Southampton on influenza, similar spike structure of the virus, and we speculated that if it worked on that spike virus, it should work on SARS-CoV-2, which is this very similar virus. And I wrote a couple of notes about that were published here and there. Ultimately, Professor Keeble was able to do an experiment on the virus that causes COVID-19, and he did find that it worked as was speculated. And we also had done some lab tests, and initially we were in discussions with the EPA, and basically there was a temporary registration for allowing claims about copper versus coronavirus. So there was something there, and it's interesting that even though COVID-19 was caused by droplets and inhalation of the droplets and people wearing masks, you could still see it applied for touch surfaces, because the droplets can land on the touch surfaces, and the human hand touches the surface, and then we're fidgety people, and we touch our nose and our eyes and whatever, and we introduce the virus into our system and become infected. So there is a mechanism for it to occur, and we believe there would be applications for it against respiratory infections caused by droplets.
Right on. And we did some work. I can't claim to have seen a lot of citations on this. So, Sammy, besides our editorials that we wrote in Corrosion Journal, we did some work. We got some, as I mentioned before, some NSF rapid funding, which stands for like emergency funding in result of COVID. And we had some surrogates of COVID-19 in our hospital, and it was kept there. They have the equivalent of these very secure rooms for the viruses, et cetera. But one of the things we studied was wanted to look at the release rate of copper, since it is corrosion and it is release of cations in these assay media that are often used by the medical community. And the real touch solution, as Harold mentioned, if you touch some surface and then rubbed your eyes, it would probably be artificial perspiration, either on the surface or probably on your hands to begin with. And so we looked at a range of those. We looked at a range from like almost 100% assay media to 100% the artificial perspiration. And by the way, in artificial perspiration, the virus lasted long enough that you could then say, okay, gee, what does a metal do? What does a plastic surface do? What does a mask do? You know, what does cardboard do? Because everybody ordered all this stuff by Amazon, of course, during the pandemic. Nobody went shopping. They ordered everything through the mail. And what we found was that, guess what? More release. There was less inactivation from SA media alone, but there was more copper release. So what happened? Well, the SA medias are so complicated. There's a lot of things in there that can be chelating agents. So there isn't much free copper. All the copper was really bound up by a strong bonder that formed a ligand that forms a strong bond that can do this chelation process. And what we found is in artificial perspiration, there was less corrosion, but there was more virus inactivation. And so it brings to the surface the idea that we need to study further how we're evaluating these materials and what we're putting them in and how that compares to the real world environments. And so that was just one little small contribution to the COVID thing. A few other things are that there is a large disinfectant business. I mean, you can buy Band-Aids that have silver dots on them and things like this. And there are companies that take basically on the fabric, they somehow impregnate one of these copper oxides or copper hydroxychlorides, and they then release it when they need to for some patient to release it. They claim that these are washable, which I find to be very interesting. So it must be use some pretty advanced technology to withstand the wash chemicals and to still be available for disinfection. But I don't think as much research as Harold has said as could have been conducted on the relationship of something like COVID-19 to these antimicrobial materials really was not realized, because I think once and there is a mask issue as far as if you have an aerosol with COVID-19, would it have a residence time on the mask that's long enough to be inactivated? So there's a lot of needs, gaps, and opportunities, I think, there. But we think once people understood that it was largely transferred by aerosols, some of the focus shifted elsewhere.
The whole idea of how things work and how do you use them is absolutely critical. We did a lot of laboratory work on copper alloys, but we finally said we have to do a clinical trial. And we did a small clinical trial at North Shore University Hospital on an outpatient phlebotomy chair, which is basically taking blood samples. It was an infectious disease clinic. And we put in just the top of the where the arm rested when they were taking the blood sample. And we found that there was less bacteria certainly present on that versus the wood surface that's coated with a laminate of plastic, and that was highly contaminated. But I said, is this going to really help? We've reduced the bacteria, but what about the infections? We had no way of tracking it. So finally, we got the funding through the Department of Defense to conduct a clinical trial. And what we did is we recruited 3 hospitals, Medical University of South Carolina in Charleston, the Veterans Administration Hospital nearby in Charleston, and also Sloan Kettering Cancer Center in New York City. We made 7 components and put them into intensive care units. These are medical intensive care units, and these people are there because they're very, very sick, and they're very prone to infections. It's not surgical intensive care. It's people that have infections. We made IV poles, the bed of the rail, a visitor's chair, and a couple of other items out of copper alloys and put them in the rooms. They only comprised, less than 10% of the surface area of the room. And we measured the bacterial loads on these surfaces, and we had other rooms that were the control rooms, the ordinary rooms with the plastic and stainless steel and what have you. And we found out we reduced the bacteria by 83% overall. We had no control over the frequency of cleaning. We just sampled each day, and that's what we found on average. And I said, but does this help? we finally got permission to track infection rates. That was in the third year of the project. We tracked these infection rates. The doctors that examined the clinical data were blinded. They didn't know if the patients were in the copper rooms or in the control rooms. And we found we reduced the infection rates by 58%, and the number was statistically significant. In clinical trials, they use a P factor, and if it's low, very low, you're in good shape, and we were much lower than 1. It was 0.017 or 1.18, something like that. So we had a statistically significant reduction in infection rate in these clinical trials, and that's the first time that's ever been demonstrated.
That's impressive. I mean, that's a huge difference between the two.
Yes. But it's interesting when I've got the docs, I've recruited them, and we're working with them, and they say, "What are you going to do? What do we do if we don't get any results or it doesn't work at all?" I said, "You publish it anyway. I'm not going to stop you from giving the real results from this trial. We've got to be ethical and tell people if it works or it doesn't work." And indeed, it worked.
That's good. And building off of that, what are some of the needs, gaps, and opportunities in harnessing the antimicrobial properties of the metals? I mean, I think that's a clear case for we should have more copper and copper alloys on high-touch surfaces in hospitals. I think that would be an easy one, but other than cost. But really, what are some of the areas?
Well, let me talk about the cost. Okay, that's interesting. I had the data. We knew how much it cost us to make these, and these were handcrafted, okay? And we knew how much it cost to treat a patient, and I did some back-of-the-envelope calculations, and we're talking about paybacks that were in months.
Oh, wow.
Okay? It doesn't have to be a big, bulky thing. You just got to get the surface covered. And it'll last for, a decade or two. So
Right,
there are ways of getting around this. And where do you use it? Your mind can go wild. Certainly mass transit systems.
Right. As Harold pointed out, there's so many ways to spray, thermally spray and cold spray and different ways to put some sort of a coating, even after the fact on these high-touch surfaces, that it's really within reach to be able to do a lot of these things. There's really sort of been an explosion of technologies that allow you to coat things in the field, let's say, certainly in the factory, but in the field. You can even envision, low temperature application processes where you could coat the keys on a computer or a copper mouse or a PDA. You can coat that. There, as I mentioned previously, there are also these anti-touch screens, and that requires a little more thinking about if you take a borosilicate glass or whatever the touchscreen glass is, incorporating the copper compounds. I was thinking, actually, Harold, you have the wisdom, all the field experience, but I was thinking that one of the needs is, some consistency in testing. And maybe there should be a variety, so it isn't one winner take all. But, the EPA protocol, I don't have to tell you that 99.9% bacteria in 2 hours. But to me, that depends on what solution. So you do it in a broth suitable for bacteria to live in, or do you do it in sweat? What about wetting and drying? All the things that are issues in atmospheric corrosion. Since it's released, copper is released by a corrosion mechanism, it seems to me all those things are important. Even the cleaning solutions, there's probably understudied. We're looking at this a little bit. If you clean a surface with glutaraldehyde, and if you clean a surface instead with bleach or just with soap, what is the outcome? How does that affect the subsequent antimicrobial functionality of the surface?
These are all very, very valid points, without a doubt. But let me go back to the EPA protocol.
Yeah, please do.
I don't know if, what is the typical surface? What is the contamination on a typical surface in a hospital? Not a copper, but let's say an inert surface, glass, plastic, wood. It's hundreds to thousands of colony-forming units. And I should explain what a colony-forming unit is. Basically, one bacteria, you take a sample and you off the surface and you put it in a petri dish and you grow it under ideal conditions. And this bacteria doubles in size, and then it doubles in size again and again and again. And then you can see it. And you can see that one colony came from one bacteria. And you count those things, and that's how you figure out how much bacteria is on a surface. We found hundreds to thousands to 10,000s or even 100,000 on a highly contaminated surface. 1,000 is 10 to the 3. The EPA protocol is 10 to the 9. Do you realize how much bacteria that is? You can almost see it on the surface, depending on what you're looking at. You can see there's something there, but you don't know what it is. That's an awful lot. That's a really, really very rigorous test. I don't think you even need that amount of killing to reduce infections, but that's what the EPA wants to ensure that people are safe. So they made it very high that only materials that could meet that criteria would be approved by them. But it's really not, you don't have to reduce that many. And certainly in the real world, we found out we reduce infection rates by a significant amount. So there is benefit. So more is better. And copper is very, very effective. But, you know, it still hasn't been taken up by society because of initial first cost, maintenance concerns, etc., fabrication concerns. But I think it has real benefits. It's a passive system, requires no human intervention, and it works all the time. Copper is a great material for these applications. It should be in, as I say, mass transit, but it should be in certainly nursing homes after hospitals. It should be in schools, public buildings, and it should be in your home. And there are so many applications, physical fitness facilities, you just name it. The applications are endless. You can just let your imagination go. And I can't think of a place that's really bad to put these materials in. They're all good. They'll all help you. It'll cut down infections.
No, I definitely agree that anything that you can do to help reduce the number of infections, even if it doesn't eliminate all, I mean, there's so many benefits to that. And anytime that you can do it even in your own home, that's a good thing to point out, that we think about germs externally, right? You leave your house and you go someplace, but it's also around your home.
Sure. Well, I just want to, we don't really track total infection rates. And they're really hard to get good studies that show you what happened. But I have something that was a government-issued study, and it showed that in 2002, which is, over 20 years ago, 1.7 million hospital-acquired infections in U.S. hospitals. Okay? Approximately 100,000 deaths, and the cost to treat these infections was $36 to $45 billion. This is the treatment cost. Just think if you took the money from the treatment cost and installed copper, you'd cut them down, and it'd be there forever. It wouldn't be there for the 1 year. It'd be there for a minimum of 10, 20 years.
Yeah, so it definitely pays for itself pretty quickly, as you mentioned earlier.
Yeah. We did another little project, a demonstration project, and the stuff for our clinical trial was all handmade, but we decided to do a demonstration project, and we did it in a Ronald McDonald House in Charleston, South Carolina, which was a few blocks away from where we did our clinical trial at the University of South Carolina in Charleston. And of course, we used the lab for an analysis. And what I did is I gave purchase orders to companies to make components. And I got sinks made by LK, and hardware manufacturers involved, people making railings. So we had commercial products, and we outfitted the Ronald McDonald House. If you're not familiar with the Ronald McDonald House, it's used for the families and for also when the children, before they go home, who are in the hospital nearby, so the family can have a place to stay while their children are going through some serious, usually cancer treatment or something like that, or it's really a very good mission, I must say. So we were really happy to do this. We outfitted it. And then I said, well, now we can't really track what they're doing. People are coming and going. But I said, let's measure the bacteria on these surfaces. It was the same thing as in the hospital 2 blocks away. So we knew what the copper surfaces and the control surfaces were, and they were virtually the same.
Yeah.
So we know it worked.
Which is good. It's great when you can kind of show that it's working. For the interest of time, I'm going to move on to our last question, which is which areas need future research? And if there's anything else y'all want to touch on needs, gaps, and opportunities, you can roll it into this question as well. And John, did you want to kick this one off for us?
Yeah, I think that one of the things is that I think that there needs to be much greater study on the effect of allying elements. I know a lot of empirical knowledge is around, and over 200 years experience, maybe more, 500 years experience, 1,000 years experience back to the Bronze Age, et cetera. But I think that there's some exciting things going on with multi-principal element alloys that are really shedding new light on what an atom does. So when you take zinc, for instance, just in Nordic gold is 89% copper, 5% zinc, 5% aluminum, and 1% tin. And so zinc actually has interesting effects. It lowers the corrosion rate. Tin raises the corrosion rate, which might make it, good for antimicrobial. But it's the idea of playing with these different elements. We're finding now in multi-principal element alloys that even things like short-range order can change the passivation. In other words, if you have 5 elements in an alloy, or even if you have fewer elements in alloy, that the elements that you put in can change the ordering. They might like or dislike the neighboring atoms, so to speak, and that will change its properties, all of its properties, including color resistance, including what oxide forms. And I don't know, Harold would have to say whether this is all marginal, because most alloys with greater than 60% copper are effective. But I do remark that Nordic gold is not, after it passivates. And Harold was the first one to tell me about this, and then we studied it with one of my master's students. I also think that the Fenton reaction, which Harold mentioned, needs more study. So one of the things you could do to a material is, can you put in allying elements that accelerate the Fenton reaction? Remember, now we're not talking about release of metal cations. We're talking about the idea of producing oxygen radicals or hydrogen peroxide. So can you squeeze more antimicrobial or antiviral capability out of the same alloy, just if you knew what you were doing with the elements? The other thing I'll mention is the cleaning issue. So I think that the idea of what surface are you dealing with, because in all of these testing, we talk about how high of a bar the EPA test is, but in all these testing strategies, we really need to know what is the surface preparation that's applicable. Obviously, something long-term in public transportation might have some corrosion product on it. It might be some porosity to that film. And I think all these things need to be understood. And then at last, I would say that things like chelators need to be understood, and then how they factor into the different test solutions that we choose. Because basically the chelators can be a game changer if they tie up all the free copper. And so that really needs to be better understood. And I'm sure there's a lot more issues. I think the dry inoculum issue is another one. So there are people that have done studies in the dry, so to speak, that aren't wet. Now, I would say that with chlorides on the surface, like magnesium chloride, things actually stay wet down 50% relative humidity or less. And so I think that needs to be considered carefully, like what's really dry and what's so dry basically that you can't liberate cations via a corrosion process. That might be one question. So I think there's a lot of exciting things to do. And I guess Harold could have a better ability of gauging which of those could have big impact and really move the needle on the dial as far as this disinfectant capability, or which are really marginal that are not worth pursuing?
The one thing we really haven't mentioned, which we discussed offline, is I've always felt, and John was very receptive, and he was thinking along the same lines, that basically we're talking about corrosion at a very, very low level in an environment. And this is, I call it nano corrosion. But it is corrosion. And anything you can do to accelerate the corrosion process to make it beneficial to mankind is what you're looking for. But you don't want it to be so radical that the component is going to wear away. So it's a balancing act you've got to play. And there's so many things to explore, as far as research is concerned. You could go on forever, but I think we've got enough to go out and help right now with what we have, and then we can improve upon them with all of these other techniques.
I think that's a great point. I mean, we can start. We can start implementing some of this now as we keep looking on ways to improve and looking for future things to do. Thank you both for joining me today. If anybody wants to follow up with you later, if they have any other questions, what's the best way for them to get in touch with you?
This is Harold. cu.microbes@gmail.com. Let me repeat, cu.microbes@gmail.com.
Yeah, and for me, it's John Scully, just JRS 8D as in Delta, at virginia.edu, virginia.edu. I'd be glad to receive an email from you.
Wonderful. And with that, I'm Sammy Miles. I'm here with Harold Michels and John Scully, and thank you for listening to another episode of Corrosion Journal's interview series. You can subscribe to AMP Podcasts if you haven't already on Apple, Google, Spotify, and all the major distributors. If you want to learn more about the journal, please make sure to visit corrosionjournal.org. You can find all episodes of AMP Podcasts on amp.org. That's ampp.org. And we'll be back soon with another episode. Thanks for listening.